that we are on now. Yes. So it takes some time for it to propagate. You are saying 0, but it takes some time to propagate over the network before you see it yourself. So how about all those things to good morning, students. Today, I want us to look at some of the things we considered the last time, so that we can get something more. Last time we talked about molecularity. I just want to repeat myself. And I want you to know that molecularity of a reaction is the sum of the stoichiometric coefficient of a reactant involved in the stoichiometric equation of the reaction. For example, in this reaction, we have 2A reacting with 3B to form 3C and 2D. The stoichiometric coefficient of A and B, because it's of the reactants, the stoichiometry of A and B are 2 and 3. And so the molecularity is the sum. So we have to add 2 plus 3 to get 5. So therefore, the molecularity of that reaction is 5. This is a simple relationship. There's no relation. I want you to know that. That's why I wrote it in red. There is no simple relationship between order and molecularity. There is no simple relationship between order and reaction. So I want to give us the differences between molecularity and order of reaction. We spoke about it, but I just want to explain it better to you. Now, the differences between order and molecularity. Order of reaction is the sum of the power of the concentration terms in the rate equation. So if we don't know the rate equation, which is got by experiment, you have to do experiment to get rate equation. So the sum of the power of the concentration terms is in the rate equation is the order of reaction. So if we write the rate equation, the power to which the concentration is reached in the rate equation is the order of reaction. Whereas molecularity is the number of reacting species undergoing simultaneous equation in the elementary or simple reaction. So it's the number of species. So that's why we talk about coefficient. Number 2 difference is it is an experimentally determined value. Order of reaction is experimentally determined. But molecularity is a theoretical concept. So once we can balance the equation, we can know the molecularity. How many molecules are reacting with 2 how many molecule of A is reacting with molecule of B? So it's a theoretical concept. We can always do that. I want you to also know that order of reaction can have a fractional value. We can have order of reaction can be fraction. It can be 1 all over 3. It can be 1. It can be half. It can be 1 all over 4. So it can have a fractional value, but it is always a whole number in molecularity because it is the number of molecules reacting. So the number of species. So, and it must be a whole number. So it is always a whole number. Number 4, it can assume a zero value. Order of reaction can be zero value. Whereas for molecularity, it cannot have a zero value. And lastly, the order of a reaction can change with the condition, such as pressure, temperature, concentration. Order of reaction can change with temperature. When you change the condition, the order of reaction can change. But molecularity is invariant of the chemical is invariant for a chemical equation. It's invariant, so it will always be the same. So I want you to note that. So because it is a theoretical condition. Now, we want to talk about collusion model of chemical kinetics. And the main point of collusion model is that, 1, molecules must physically collide in order to react. That's number 1 point. So for collusion model, the molecules must physically collide in order to react. It's just like in our relationship with one another. If we don't meet each other, we cannot be friends. There must be something that will make us to collide with each other, and they must be physically collide in order to react. Somebody cannot be your friend, if you don't meet him. If you have never met a person, he can be your friend. Either you meet in class, either you meet on the corridor, in the hostel, somewhere, or in the practical room, you meet. Physically, you collide with each other. So molecules must physically collide in order to react. Number 2, the more collusion that occur over a given period of time, the rate of reaction. So the more collusion we have, if molecules continue to collide with one another, the faster the rate of reaction. And you can see that there are some people, you don't like them the first day you saw them. You kept on meeting, after some time, you discover there are some good things in the person. You discover that the person, he has some good point too. I like this part of him. I don't like this part of him. And then bonds start forming, and there is a reaction. So the more collusion, the first collusion might not lead to reaction, but when more collusions, so that's why the more collusion that occurs over a given period of time, the faster the rate of reaction. So, because when you collide, most of the time, you will discover, oh, this is a good person. This is a good person. And then you start relating. Now, let's look at it. Increasing the concentration. So, if we increase the concentration, that is, if we can increase the concentration, we'll increase the number of molecules in a given volume. When you increase the concentration, you increase the number of molecules in a given volume. It will increase the number of collusion. And the result is a fast rate of reaction. So if you increase the concentration, and that's why when you increase the concentration, the molecules collide more. That will be increase in the number of collusion, which will result in the increasing the rate of reaction. So, and when we were discussing effect of concentration, we talked about that. So more molecules, when the concentration increases, the molecules collide more frequently, and the reaction will be faster. And I want us to note that. Now let's look at molecular collusion resulting in reaction. I want you to know that when molecules collide, it doesn't automatically lead to reaction. Not every person you meet will be your friend. There are some people you collide with, you met, and you hate them more. So there is no bond forming between all of you. And so everybody goes his own way. So now let's look at this molecule. For molecules to form a reaction, they must come together in proper orientation. Look at NO and NO3. That's the molecule. This is NO3. This is NO. When they collide like this. You will discover that the oxygen over here, when they collide, there is no bond between them. So everything remains the same. So there is no reaction in this one. There is no reaction. So the reactant, it goes back to reactant. Even though they collide, but it goes back to reactant. So this collusion is not effective. Look at this second one. If there is a blue one, I mean that nitrogen collide with this, they will collide and form this. And so it will go back to itself. These are two ineffective collusion. They are two ineffective collusion. If they collide like this, with red coming this one or blue coming this one, they are ineffective. But let's look at the effective collusion. When they come like this one goes like this and collide at this point. This oxygen will join to the nitrogen and they will form NO2. And the remaining two will be oxygen. And so this is an effective collusion. There is effective collusion. So on the overall, what we are saying is that not every collusion will lead to a reaction. And from your normal thing, not every person you meet will be your friend. Some of them you even hate more. You go your own way. Everybody goes his own way. It means your relationship is ineffective. There's an ineffective collusion. But when you do this, it will be effective. And so bonds will be formed between this and this. And so it will form NO2 and this will form oxygen. And so this is an example of how molecules, if they are not properly oriented, when they are colliding, it will be, there will not be any effective reaction. You know that some people you meet, the way they talk just irritates you. So that would be an ineffective collusion. It can't be your friend. You don't like people who talk this way. But there are some people, when they talk, you just like them. That's an effective collusion. So I want us to know that. So there must be proper, they must come together in proper orientation. And I want you to note that. Number two, colliding particles must have sufficient energy to initiate the reaction. Energy to break relevant bonds or to form relevant bonds. So when molecules collide, when molecules collide, they must have enough energy to initiate the reaction. It's just like in any relationship, especially people getting married. If the person you think you want to marry does not have enough money, that's the energy. It doesn't have enough money, that marriage will not take place. So when particles collide, you know, they collide with energy. They must have sufficient energy to initiate the reaction. If the energy is not enough, it might have increased, but if it is not enough to cause the reaction, what will happen? They will break. So which means it's not an effective collusion, because the energy is not sufficient for them to react, for the reaction to take place. And I want us to note all these 2 points. So a reaction, number one, it must collide with proper orientation. Number two, they must have enough energy to initiate the reaction. If there is no energy, there won't be any reaction. And I've related it to marriage. If you want to marry somebody and he doesn't have enough money to even do marriage, he doesn't have money to even start the party. Are you getting what I'm saying? that type of, it doesn't have enough energy. Even though you collided, it was good orientation, but it doesn't have energy. What will happen? It will bounce back. So I want you to note that very well. Before we continue, let me give you the attendance code. 1. This is 9 N Q G D. I repeat myself. 9 N Q G D. For the last time. 9 N Q G D. That is code 1. Now let's more. We want to talk about activation energy. In 1888, a Swedish chemist, Arrhenius, proposed the following. He said, molecules must possess a certain minimum amount of energy in order to react. So he's telling us, the second postulate of collision is telling us that for molecule to collide and get result, they must have certain minimum amount of energy in order to react. And they say that the minimum energy needed to cause a particular chemical reaction is called the activation energy. It's called the activation energy. So for two molecules to come together, when they collide, they must have what we call activation energy, energy that will initiate the reaction, that will cause bonds to form, that will cause bonds to be broken. This is what we call the activation, which we call EA, is the activation energy. And that is the energy that we needed, that molecules needed in order for a reaction to take place. Activation energy. So we have said that for a reaction to take place, it must collide with proper orientation. And secondly, they must have energy. They must possess energy. When they collide, the energy they possess must be, the minimum energy they can possess will be the activation energy, that minimum energy needed to cause a particular chemical reaction to take place. Now, let's look at the diagram. This is the energy. This is the molecule is going to be. The molecule goes, they collide with each other, and their energy will be increasing until they get to that minimum energy. This is the activation energy. That's the minimum energy, the activation energy. It is this minimum energy that then they will react to form B. So for any reaction A to get to B, they must undergo activation energy. That the energy, and they must have that minimum energy, and then they will go. If they don't have, if they get over here and the energy stops, they will bounce back. They won't get to the reaction. So delta E for the overall reaction. This reaction is energetically favored with this one. The way it goes, it shows that the energy. Can you see the reactant has a higher energy than the product, and so it's energetically favored. This is the activation energy. So I want us to look at the activation, and that's the minimum energy that a molecule must possess in order to form a reactant. So it will form B as a result of undergoing this energy. So that you see, when they collide, the energy will be increasing until they get to a minimum energy, which is the activation energy, and then they come down until it comes. So you can see this will be the heat of reaction. the energy difference between the reactant and the product, which you must have done in thermochemistry, taught by Professor Ogunlusi. Now, Arrhenius equation. You know, I told you it was a Swedish man, Arrhenius, who was able to get us that there must be a minimum energy. And he was able to calculate what the minimum energy, and he was able to find it out that it is the activation energy. Arrhenius studied relationship between increasing the reaction rate and increasing temperature. So it was increasing the temperature, and the reaction is increasing. The increase in the reaction rate, K, is not linear with temperature. You can see it over there. It's not linear. It goes like that. It's not linear. It's not a linear relationship. It goes like this. So he was able to look at the rate, the K rate constant, against the temperature. As the rate constant increases, as the temperature increases, the rate constant increases. But it was not a linear relationship. It goes that way. And so the relationship between the reaction rate and temperature was found by Arrhenius. And he found it to be equal to K, which is the rate constant, A, and then E is the activation energy, R is the gas constant, and this is the temperature in Kelvin. And this is the Arrhenius factor. A is the Arrhenius factor. So this is the equation that relates the rate constant with temperature. And so once the rate constant K increases, the rate of reaction will increase. And so you know the rate of reaction from this one. You can see that the rate of reaction will increase as the temperature increases. Though it is an exponential increase. You can see it's an exponential increase, not a linear increase. So it's an exponential increase. So we can see that. And I want us to note that very well. It's not linear at all. So it's an exponential increase. And I know you know your maths, so this is an exponential increase. So initially, when the temperature increases, there won't be much increase in the rate. But as time goes on, as the temperature increases, it will start going until it gets to a place like this, where it will just continue to go like that. And so this is the exponential increase. So, but we can make Arrhenius equation to be linear. Mathematically, I know some of you know maths more than me, but if we take the natural log of both sides of the Arrhenius equation, you know the Arrhenius equation is this. If we take the natural log of this, what will come out with is this. It will be a line of K, which will be equal to EA minus EA RT plus line A. So you can see this is the equation. You can see the equation. If we take the line of K, this will be a minus E because it's raised to E. It will go minus E plus line A, where A is the line of the Arrhenius constant. And so if we'll take the line, it can be equal to this. So if we look at this equation, if you want to make this equation a straight line equation, this will be Y. This will be the M, and this will be X because we are talking about temperature, and this will be a line of a B will be line of a. So this is straight line equation. And so if we plot it, it will be a straight line. Line A all over 1 all over temperature in Kelvin. It will, if you plot it, it will be like this. So if we look at the intercept of this, it will give us line A. It will give us a line A. It will give us line A. And the slope will give us it will give us all of this. So if we know R, we can get if we know R, we can get the gas constant, which we know is a constant. We can get the activation energy. So from this graph, we can get activation energy. So this is how Arrhenius was able to find the activation energy, the minimum energy that is required for any particular reaction to take place. So this is how he found the activation energy. And I want us to look at it very well. I don't know if there is any question about this. I don't know if there will be any question about this before I continue. Nobody is asking question, but you all need the code. Attendance code is what you are talking about. Okay. Let's continue then. Another form of Arrhenius equation. If we want to know the reaction rate at two different temperatures, you want to at temperature T1 and at temperature T2, we can calculate the activation energy without knowing the value of the frequency, without knowing Arrhenius factor, or what we call frequency factor or Arrhenius constant is A. That's what we call the frequency factor A or Arrhenius constant. So take, for example, we'll take the log of K1. It will give us this. For the we can, in terms of T1, and then we can do the log K2 in terms of T2. Now, if we subtract this equation from this equation, what we will have will be K1 all over K2, ER all over this. We can get T1, T2 all over this one. This is what we'll get if we subtract this one from this one. If we subtract this one from this one, that is line K1 minus line K2. That's what it will give us. This is mathematics. You should try and to work it and see how we will come about it. So try to work it. Try to do the mathematics. I'm a chemistry teacher, but I know maths, and you have done maths 101, and so you should be able to do that. So I want you to try it and be able to, how this one gets to this one. And so with this one, you discover that if we subtract this one from this one, this will cut this one out. And so we don't need to know frequency factor A before we get Arrhenius equation. Unlike the other method we use, we have to know the frequency factor. But in this case, we don't need to know the frequency factor. If we know the temperature at one particular time, and we know the temperature, and we know the rate at different times, at those times, you can calculate the Arrhenius equation without knowing frequency factor A, which is the Arrhenius constant. So there will be some problems we will work that will determine that. Now let's look at the first example. The first example says a reaction has EA, that's the activation energy of 84 kilojoules per mole. What is the effect on the rate, all other things equal, of raising the temperature from 20 degrees to 30 degrees? In this case, they are moving from 20 degrees centigrade to 30 degrees centigrade, but we have the activation energy. But what are they asking? What is the effect? What will happen? Will the rate increase or will it decrease when the temperature goes from this to this? By what factor? This is what they want you to know. So we know the temperature, we know the T1, and we know T2. We know the activation energy. Now they ask us to calculate what effect will it have. So, but we need to calculate. We just can't say, oh, because the temperature is increasing, it must increase. So, but we must, by what factor? We must be able to get it in order to do that. Now let's look at it. You know, the temperature T1 is 20 degrees centigrade, but we must add it to Kelvin. We must change it to Kelvin. 273. That would be 293. And then T2 is 30. 273 plus this, it will be this. This is T1. This is T2. Now we know that 1 all over T1, 1 all over T2 will be equal to 1 all over this minus this, and it will give us this. Now, from the equation that we got, this one, we know that like K1 all over K2 will be equal to E all over A 2.3035 RT. But we know this. We have just calculated this. The whole of this is this. So we can just substitute into this equation. And this is what we have. So you discover that when you, this is line K1 will be equal to this, but K1 all over K2, it means that it will increase by a factor of 3.13. Can you see? It has increased the rate constant. I mean, the rate has increased by this factor. When you're K all over K2. So the rate constant has increased by a factor of 3.13. So this is what they asked us to find. What effect will it have? It means the rate constant will increase by a factor of 3.13. If you don't calculate this, you can't just say, you can't just imagine that to it. But I know you are going to do multiple choice exam, but you must know what you are doing in order to get this. Thank you very much. Now, let me give you the attendance code 2. Attendance code 2 is M D G 6M. I repeat myself. M D G 6M. I will repeat it for the last time. M D G 6 and M. That will be the attendance code 2. And I want us to do it on time so that we can Now, I'm giving you this assignment, and I want us to look at it so that you can try it on your own. Assignment 3. I've given you so many assignment 2. I've given you assignment 1, assignment 2. I hope you are working there. This is assignment 3. It says, at what temperature will the rate of a reaction be 3 times that found at 20 degrees centigrade? All other things being equal. We were given the activation energy. You know, in this area, in this question, this assignment, they want to know what temperature will the rate of reaction be 3 times. So we know K1, K2, K1, K2. K1 must be 3 times that of, K2 must be 3 times that of K1. So the rate must be 3 times. And the initial temperature is 20 degrees centigrade. So from that equation, we can just substitute. We know E. If we look at the equation that we use, this equation that we use, we know this one as T1. We know the T1. We don't know the temperature of this, but we have the activation energy. We know this. It will be 3 times, 3 times of this. So you can know log of 3 times. So from that, you can calculate the temperature. You can calculate T2, which we really wanted to do. So this is how I will love you to work this problem. and try your hands on it, because there will be some things for you to do. You know, the last thing I want to talk in this lecture, and I'm sure, I hope this today will be my last lecture from the way we are moving. Effect of catalyst. You know, we have talked about what are the factors that affect the rate of reaction. We have talked about surface area, concentration, temperature, pressure, but we also talked about catalyst. And so we want to talk about a catalyst. A catalyst is a substance that changes the speed of a chemical reaction without undergoing a permanent chemical change itself during the process. So the catalyst is not used up. It just initiates the reaction and the speed of the reaction to increase. I want you to know that without undergoing permanent chemical change during the process. A chemical reaction may be energetically favored, that is, may be exothermic. But if the activation barrier is high, the activation energy is high, the rate of reaction will be extremely slow. So the activation energy will determine whether the reaction will be fast or it will be low. So a reaction can be energetically favored, but if the activation energy is high, then what will happen? Reaction will be extremely slow. And I want you to know that. Now, the Arrhenius equation states that the rate constant K of the reaction is directly proportional to the frequency factor A. That's the frequency factor A, or some people call it Arrhenius constant. Is inversely proportional to the activation energy, directly proportional to the temperature. So we have talked about this. This is the Arrhenius equation. Now, if a catalyst is to increase the rate of reaction, okay, it will appear to be able to do so by one of the two ways. Number one, it can either increase the frequency factor A or decrease the activation energy. So a catalyst, what catalyst will do is either they will increase the frequency A, that is, it will increase the rate of collision. It will increase the rate of collision, or number two, it will decrease the activation energy. So if the activation energy is decreased, the reaction will be faster. There will be more energy to overcome. There will be less energy to overcome. So generally speaking, a catalyst typically increases the rate of reaction by lowering the activation energy. Because there is no way the first one will not affect, because the molecules collide at a particular temperature, because we are talking about a particular, the temperature, they will collide with the same frequency. But the only thing that will affect it more is the activation energy, by lowering the activation energy. So what catalyst does, it lowers the activation energy. So the energy for you to overcome the barrier is less. And so more molecules will be able to and the rate of reaction will increase. And this is related to is related to energy required to stretch or break bond. Thus, catalysts must facilitate this process in one way or the other. So I want you to know that. I want you to know that catalyst will lower, what it does is to lower the activation energy. Now let's look at it. This is the energy. These are the reactant. Without catalyst, the reaction goes this way. with a black distance, and it forms the product. But when a catalyst is added, it lowers the activation energy. Can you see? The activation energy is lower. It's not as high as this. And so more molecules will have that minimum energy. You know, it's just like a person who wants to get married and is maybe he's 25, he has more years, or 20, he has more years. But after some time, he gets to 25, 26, he's not yet married. Maybe his standard was that, oh, before I get married, the man I will marry must have a car, must have a house, must do this, must do this. But when he's getting old, people will have to tell him that, look, lower that standard you are trying to build. And if he lowers the standard, more men will come and he will like them. So the activation energy has been reduced. So because the activation energy is reduced, more people can collide and get enough energy for the reaction to take place. And so the reaction becomes faster. And so these are some of the, so in catalyst, can you see, without catalyst, the activation energy is high. Can you see the activation energy is very high? But with catalyst, the activation energy is lower. And so that's why the reaction becomes faster. So what catalyst does is to lower the activation energy, thereby making the reaction faster. There will be energy in order to facilitate the reaction. So the reaction becomes faster as a result of lowering of the activation energy. Also, a catalyst often lowers the overall activation energy for a reaction by providing completely different reaction mechanism for the reaction. It can lower the activation energy for a reaction by providing completely different reaction mechanism for the reaction. In other words, a different set of underlying elementary reaction steps. It will provide another way that will lower the energy, that will not be another pathway that will be easy for him to overcome. And this is some of the things that we need to know that catalyst does in the rate of reaction. So catalyst does not just increases the rate of reaction by allowing them to collide. They collide normally, but it lowers the activation energy and makes the reaction faster. Now let's work this example, and I'm sure this will be my last example for this class. But before we go into this, I will want to give you the attendance code, then we'll solve this problem. And I want you to record it before the end of the class. The third attendance code is A3NG. A3NG. For the last time, the attendance code is AA3NG. I don't know if there is any question you want to ask. I'm only trying to see. Somebody said, what is RXN reaction? It means reaction. RXN means reaction. It means reaction. So I'm only trying to. It's not ER, it's RXN. That's reaction. It means reaction. And the code is AA3NG. It seems there is no question. I will continue my lecture. Let's work this last problem. A reaction is found to have an activation energy of this. We were given the activation energy at 25 degrees centigrade. On addition of catalyst, the rate speeded up by a factor of 10 raised to power 6. What is the activation energy with the catalyst? So when they added catalyst, the reaction becomes faster by 10 raised to power 6. So that's a lot. What is the activation energy with the catalyst? You want to know the activation energy when the catalyst, the catalyst will lower the activation energy. So we want to know what will be the new activation energy as a result of the catalyst. Now, look at the solution. Suppose K1 is the rate constant in the reaction, and K2 is the rate constant of the catalyzed reaction. So K1 is the rate constant of the reaction, and K2 is the rate constant of the catalyzed reaction. EA1 is the activation energy, while EA2 is the activation energy in the catalyzed reaction. So we know that. So we can write the two equations. For the when it's not catalyzed, the first equation is this. When it's catalyzed, the second equation is this. If we subtract this from this, it will be K2 minus this, log of this, and it will give us this. I decided to work it for you this particular time. So this one will be subtracted from this, so this will be this. Now, let's move further. I hope you can get what we did over here. We only put this one, K2 minus this one, and so the whole of this will be minus this one. And that's what we have got over here. So that will be minus here. So that will be, so with a bracket. Now, when you open the bracket, this becomes plus. And so this is what will happen. And so they have both denominator. They have the same denominator. So everything will be here. I can't teach you this math. This is mathematics which you need to know. And so if we look at the rate, this, and the log is going to be equal to this. So this will be equal to all this. And we know all these ones. We know E1, we know E2. We don't know E2. This is what we are asked to find. So we know E1, which is 50 times 10 raised to power minus 4 because it's kilo. And then this one will be this. And then the rate is 10 times the raised to power that. When you find the log, it will be 6 over this. And so this is what you get. And from that, we can get what our E, which is the activation energy. And so when we do this, it will be the activation energy will be this. So the activation energy has been lowered. Can you see? It has moved from 50 kilojoules to what? 1.6 kilojoules. Can you see? To 16 kilojoules. From 50 kilojoules to 16 kilojoules. So you can see that the activation energy is very low. Very low. And so the reaction becomes very fast. Thank you for listening to me for the past 4 lectures or 3 lectures that I have with you. I think I'm through with you. I wish you all the best in your exam. Have a wonderful day. God bless you. Thank you. Thank you, sir. Let me congratulate you, sir. Yes. Because I enjoyed your delivery. Thank you. Yeah, you know. Oh, it's off. Yeah, okay, thank you.